Hi, everyone, and welcome to another talk in the general track. Just yet another reminder about the chat window on the right. Go ahead and type your chats in there. But if you have a question for the speaker that you want to ask at the end, please raise your hand. That's a great way. I'll invite you up on stage and you can ask them yourself. And then the Q&A, if you prefer to just type out your question, then click that Q&A tab and write it in there as opposed to the main chat window. And I'll show your questions at the end and ask the speaker myself. And that's it from me. Please welcome Tim.
Hello, thank you very much. So my name is Tim Matson, and this is work I've done with Todd Anderson. And Todd Anderson is going to be online right now following the chat. So feel free to ask him the hard questions just as the talk is going on. So I have to tell you, I'm darn excited. This is some of the most exciting work I've done in several years. We figured out how to put OpenMP into Python. And if you do HPC, that's a big deal. At least I think it is. So let's go ahead and launch into this presentation. Here's the official do not sue Intel note. This is the big disclaimer. I want to emphasize Todd and I work in a research organization. We are not official spokespersons for Intel. No lawyers or marketing people have blessed these slides. As I like to say, if we say something smart, it's because we work with smart people. If we say something stupid, it's our fault. And I really emphasize, we're not describing a product. In fact, it's our job to get ahead of the product group and think of what could be the products in the future. And in that regard, we're really eager to hear from you. If you listen to this and go, yeah, we want this, let us know. Because this is kind of the first public airing of what we've created here. So we're going to talk about motivation. I'm going to give you the fastest introduction to OpenMP in the known universe. We'll talk about how we implemented this, and then we'll talk about some performance numbers. So off we go. And I want to start with something that kind of rubs some people the wrong way, but it's important to my motivation. And that is, how does the HPC people think about the Python world? And a good example of this was a paper that came out. There's plenty of room at the top. This paper's been a real conversation starter, and it's a good paper. It basically points out that, since 2005, when Dennard scaling ended, what happens at the semiconductor side, the bottom, is less important to performance than what happens at the top. And at the top is where you do software algorithms, new hardware architectures. There's a lot of room up there for improvement. And these being software people mostly, they focused on algorithms. And they use this one right here at the top, this matrix multiply. Now let me emphasize, we're looking at this as a proxy for user-written triply nested loop code. We all know, and the authors of this paper know, that if you want to do a DGEM, a double precision general matrix multiply, you do not write it like this. It's actually, if you haven't done it before, it turns into somewhere between 5 and 20 pages of really ugly code. We all know that. Okay, so this isn't about how to do a fast matrix multiply. It's like, this is an exemplar of how people write nested code. And they track the fraction of peak and look at their Python number. And I can just hear the HPC people in them chuckling at, oh, look at silly Python. Because within the units of significant figures, it's 0% of peak. And this is consistent with how HPC people think of Python, that Python it's productive, it's great for algorithm development, and it's good for managing high-level workflows. But gee, if your goal is really performance, you figure things out in Python, and then you recode in a grown-up language like C. Well, I'm here to tell those HPC people to go shove it, because we believe, and this is the dedicated work of our group, that given the state of modern software technology, why can't people keep their code in Python? Why can't we get just as much performance out of Python as you can out of C? And I know there's a lot of challenges. There's a lot of work to do to make this happen, but darn it, we can keep people in Python. And so that's what we're trying to do. And this is efforts that go back quite a ways for us. We actively contribute to Numba. Todd has done some wonderful work on Parallel Accelerator, which is a tool incorporated into Numba that looks at patterns in the code that it can implicitly realize should be parallel and transforms it into parallel code. We did some nice work on creating a scalable data frame compiler, the high performance analytics toolkit, which is really, really effective for speeding up data frames code. And then much, much more recently, since Intel's now really big in the GPU product planning world, is now we have a data parallel Python tied to Numba once again, which lets you, from your Python, generate code for a GPU through SYCL. So the point I want to make is, this isn't just a one-time flash in the pan. No, this is a long-term research agenda we have with the end goal of keeping everything in Python. So how do you get high performance in a modern CPU? Look, there are three simple principles. For a CPU, you better have a lot of threads. You better have at least one thread per hardware thread. And there's usually on the order of 2 hardware threads per core. So I show 4 cores in this little picture. But remember, you easily have systems of 20, 30. You put 2 processors in there, 40, 50. We're going to have 100 core systems. Those core counts can get up there. And then we're not going to talk about it, but there's these vector units, the SIMD lanes of a vector unit. You better keep them busy, and then you better make effective utilization of the cache. This is the foundation of getting performance out of a CPU. And when people talk about performance problems with Python, it's because Python has a hard time doing those 3 points. So when we talk to people about this, a common comment comes up which says, well, why don't we just keep this embedded inside NumPy? People know about NumPy. They'll call NumPy and everything will be fast inside of that. I want to emphasize there are 2 problems with that. Problem number 1 is that means every time you enter the NumPy function, you have to spin up and spin down the threads or whatever parallel infrastructure you're going to use. That increases overhead. And due to something like Amdahl's law, which in an hour-long version of this talk I'd go into, but it severely limits scalability. It's really bad. But another thing that HPC people have been exploiting for many, many years is when you just put the parallelism inside a set of functions, you lose the opportunity for expressing parallelism between the functions. And so I really need the ability for explicit control of threads up there at the programmer level in order to get all the performance I can. So we want threads. Problem is the global interpreter lock. Basically says, yeah, you're welcome to create threads in Python, go for it, but they can't run in parallel. And there's plenty good reason the GIL is part of the design of Python. I'm not taking pot shots at the Python design, but it's definitely what you wouldn't do if you wanted parallel multithreading. So we want parallel multithreading. We want to run many threads on the CPU in order to run code in parallel. And in HPC, there's a standard way to do that. It's called OpenMP. So here comes the fastest OpenMP tutorial on the planet. OpenMP, it's a bunch of directives that tell the compiler how to generate parallel code. It's old, and we basically created it to make writing multi-threaded code as simple as we could. And it focuses on Fortran, C, and C++. Now, the fundamental execution model between OpenMP is called fork-join parallelism. So you have the main thread. I'm sorry, we don't use the word master anymore. We have the main thread running, and then when it needs additional threads, it'll create a team of threads. And when it's done, it'll join those threads. So you get a fork to create the team of threads, a join to end them. And so you just go through your program, and where you can use threads, you put in these constructs called parallel regions to create teams of threads and run the code across the teams of threads. And it's interspersed by the sequential parts. And you can even nest parallel regions. All right, so we're going to talk about OpenMP, and we're going to explain how it is in the Python OpenMP we've created. And we're going to do it in terms of the 3 fundamental design patterns of OpenMP. And what I love about OpenMP is if you understand these 3 design patterns and the subset of constructs that goes into using them, you're ready to go. It's really, we tried to make it simple. So I'm going to use the hello world of parallel programming. It's the numerical integration. And if you get this integral right, the answer equals something that looks like pi. And there's the code at the other side of the screen. So let's talk about the loop level parallelism. So you find your compute intensive loop, okay? Well, here we only got one. It's that for loop over I in range num steps. And what you're going to do is you're going to find the concurrency and expose it by removing loop carry dependencies. So look at how I've done x. X plus equals step. Now that's a loop carry dependence. The loop iterations can't run independently. So I just recast it to compute from I. So this is what I mean by exposing the concurrency. And then I'm going to, and then there's this more complicated concurrency I'll talk about on the next slide, dependency, and it's called a reduction. And I'll talk about in a moment how we deal with that. But you put this all together, and here is a working multi-threaded program for that Pi program. And so, you know, we have to import from the Numba optimized or modified to support OpenMP. And we're going to have an OpenMP context manager, and we're going to expose it with the with statement. And that material there in the string in the quotes, parallel for private x reduction plus colon sum, that is straight out of the OpenMP specification. So if you already know OpenMP in C or Fortran, then you now know OpenMP in Python. So parallel says create the team of threads. For says map the following loops iterations onto those threads. Private with takes a list of variables, and it says here each thread has its own copy of x. The reduction says everyone's going to work on their own copy of sum, and then when everyone's done, we're going to combine it into a single value using the plus. So really easy and beautiful and elegant, and I love it. This is why OpenMP is so cool. And the performance blew me away. When I saw these performance numbers, I was just shocked. Because remember, you know, we're kind of used to thinking that Python runs slower than C, but we pretty much got the C Python performance here, which is pretty exciting. And that's because, of course, Numba is taking things down into LLVM and then compiling that. So that's where a lot of that performance comes from. And we're just hooking into the OpenMP that's built into the LLVM dialect we're using. So really, really nice. And it scales well with a number of threads. So the next pattern, and this is probably the single most common pattern in all of parallel programming. It's called the single program multiple data design pattern. And you just think of it, you have a single program and a bunch of data. You're going to make multiple copies of that program. You're going to have to do a little bit of glue code to get them to work together. You break up the data so each program gets a different chunk of the data to work on. And this is the heart and soul of how people write MPI, and actually an awful lot of OpenMP. Now, of course, things aren't as pretty because everything's very explicit. And here's what I mean. Here's the Pi OpenMP version of this. So you recognize we get the context manager. We need to use in an SPMD program, you have to know how many threads there are, and you need an ID for who you are. So I'm going to use the runtime library functions, OMP get num threads, so that tells me how many threads there are total, and OMP get thread num. That's my ID, which is a rank ranging from 0 to n-1. And this is the code. I guess the other thing new in here is the single. Single says one thread does the work, everyone else waits until that thread is done. And then I split up this loop. I use a cyclic distribution trick. I don't have time to go through it in more detail, but basically this is what you would write for the SPMD program. And then, and the performance, once again, wow, we're getting darn close. It's not a perfect match. It's a little slower than the C, but we're definitely in the ballpark of the C code on this. So that's really cool. And then the last pattern I want to mention, and I'm running out of time, so I'm just going to go really fast. This is the divide and conquer pattern. This is at the heart and soul. When you hear people talk about cache oblivious algorithms, this is the pattern they're using. So you split up your problem into smaller and smaller subproblems. You get down to a certain size, you do a direct solution, and then you merge everything back together. And you have 3 opportunities for parallelism. You can do the split in parallel, the solve in parallel, and the merge. And this is what the Pi OpenMP code looks like. And so starting at the right side of the screen, only way to create threads is with parallels. You have to have a, with parallel. And then I have the with single, so one thread launches this process. So now I'm going to call this function PyComp recursively. So I drop into this function, and there I check if the size of the problem is small enough to directly solve, if the number of blocks is less than min block. If that's true, I just do the direct solve. If it's not, I'm going to create two explicit tasks. So this is the task construct. And it basically packages up the work and puts it on a queue for other threads to call. So I have one task on half the domain, another task on the other half of the domain. I defer those, and then I wait until they're done. Okay, so who's going to do the work? Well, remember that single? One thread does the work inside the single. The other threads hang out and wait. Those other threads hanging out and waiting will do the work of the tasks. This is an extremely flexible model of parallel computing. Lets me handle recursive functions, while loops, which are important because they're uncountable iterators. It covers a very wide range. And once again, we're in the ballpark of the C code. It's actually pretty darn good. Better than pretty darn good. Better than I ever dreamed when we started this project. So I'm very excited about the sort of performance. So right now, if you follow me, you all are OpenMP programmers. You know how to do it. Now, this is it. This is PyOpenMP. It has everything: forking the threads, sharing work between threads, synchronization, managing your parallel loops, the data environment, that's that private and shared and such, and then the small number of runtime libraries, and then the way to tell the environment how many threads to use. This is the complete list of the API. So the idea is keep it minimal and simple. So I'm very excited and well, kind of proud of what we come up with. This is awesome. So let me talk a little bit about how we implemented this. So it's tied to Numba. And so here's sort of the overview of how it all works. So we use Numba to generate the regular Numba IR. And remember, we have the context managers with that string that describes what to do with OpenMP. So Numba just generates its IR with the OpenMP context managers. Now, when you look at this figure, we have blue boxes, red boxes, and purple boxes. The blue boxes, we basically did little or nothing to. That's just the standard openly available Python ecosystem components. The red is stuff that we had to do ourselves. Okay, wait a minute. Let's be honest. Todd had to do himself. So if you have hard questions about this, go on the chat and ask Todd. And then the purple is we need an LLVM enabled with OpenMP. And we used the Intel dialect, the Intel LLVM. So then you have two steps here. You go from the Numba IR with an OpenMP context manager to the Numba IR with the OpenMP nodes. Then you go to the LLVM. So those are the two big steps. And I want to say a little bit more about them. So we convert the OpenMP context managers. You've got that string, which defines the OpenMP directive. And then you have the blocks of code that the basic blocks inside that region. So we use the LARC LALR parser to turn the OpenMP string into a parse tree. And then we go up from the bottom with a post-order traversal, and then we find the private clause, and we add tags for the private variables. We find the shared clause. We add the tags defining the variables as shared, and then we get up to the parallel. And then we go through and the variables that are defined inside the code for that region, we go ahead and assign them to their status, the right tags. Now, this is important because OpenMP, we're doing the boundary from a dynamic language like Python to a fairly strongly typed dialect of C that maps into LLVM. So the challenge in all of this is keeping track of the variables and where do they go with respect to the threads, private or shared. Private means each thread has its own copy. Shared means all the threads can see it. So then we had to do the second step where we went through and we went from the Numba IR to the LLVM IR. Now, there's a little subtlety here, and you notice that on the left side of the screen, we got that curving red arrow that goes from the end to the start. So we have to keep a pointer to go back up to the start, because the challenge here is that as you do the conversion from Numba IR into LLVM IR, you might create temporary variables. And those have to also, if they're going to work multi-threaded, those have to also be properly classified as private or shared. So the PyOpenMP system had to go back after it's done generating all the code, go back once more and find any temporaries, any new variables created, and get them properly classified. So that's what it took. Now, there's a few other low-level details. I don't have time to talk about them. They're not a big deal. They're in the slides. So let me talk about performance relative to C. The performance we've talked about so far was with such short, little itty-bitty code, they don't really mean much. So we needed something juicier, and hey, let's use the same thing the view from the top people did. So we made one change up front because anyone, I mean, come on, way back when you learned about matrix multiply in 3rd grade, didn't you learn that the IKJ order is faster than the IJK? I'm sorry, the IKJ order is faster than the IJK. So, you know, the outer product order is faster. So we made that swap. But other than that, we're just playing around with that code. And so this is what the PyOpenMP double precision general matrix multiply looks like that we created. And at this point, because you're all OpenMP programmers, you recognize that. Yeah, with OpenMP, parallel 4 private, bam, there you go. That's it, matrix multiply. And here's the performance comparing to C. And the C code, basically, we use the same approach, a single directive that was pragma OMP parallel 4. And you can see, darn, we're getting pretty close to the C. I never expected this. Nobody I talked to in HPC would expect this. This is friggin' phenomenal. So we matched the performance. Wait a minute, did we? Did we match it? You know, I've studied statistics. You know, is it fair to say match? Well, okay, let's look at this. Can I really say we matched? And okay, I did good statistics, all right? We did 250 runs of each one. We computed the standard deviation. Here's the overlapping Gaussians. Is that 3% statistically significant given the variation in the data? And I'm sorry to report that it is statistically significant to within 99.99% confidence. So, no, we do not match C. We are 3% slower than the C for all that matters. But I do have to pick my words carefully because this is SciPy and Sci is science. And scientists, if they do anything, they do their statistics right. So anyway, bummer. We didn't match, but we're darn close. All right, so let me wrap up here. So basically, if you're in the high performance computing world, and you do explicit multi-threading, you probably use HPC. It's been around 25 years. You know, I guess there's maybe some of you out there listening to this who weren't born when OpenMP was created. I had the privilege of being one of the people creating it, so I've had a lot of years with OpenMP. So what we've created is what we're calling a research prototype. It's not a product, and it's tied to the Intel LLVM. It's not a product. But it's a proof of concept. We know that we need a proper benchmarking paper. Okay, we know that. We know we haven't done that. I take benchmarking very, very seriously, and we will be doing one with Dask and Ray and MPI for Pi and, you know, the other big ones. And I'll talk more about benchmarking to anyone who wants to know. Most people do it wrong. I do it right. And finally, we're painfully aware that right now you have to have a license to the Intel LLVM layer in order to use what we've created. And that is not acceptable. We do not believe that's acceptable. Intel does not believe that's acceptable. Intel is really about getting things out there open that you can just grab and work with. So we still have to work out, do we have to use one of the other open LLVMs? Can we get Intel to upstream their own OpenMP-enabled LLVM? Is the LLVM community even interested in taking Intel's upstreamed OpenMP-enabled LLVM? So there are a lot of things we're working through on what's the back end we're going to use to all this, including perhaps tying it to MLIR. So stay tuned. But I really want to hear from you. If you look at this and go, yeah, I work in HPC and I would really, really like this. Because the more feedback we get to that effect, the more we can get Intel to actually spend money to do these last few steps. So thank you very much. I think I'm on time.
Perfectly. Thank you very much, Tim. Right, we've got some questions. Let's see, I'm going back. All right, let's show this one. Is it possible to use this while also caching results of expensive functions that are run in parallel?
Yes, that's why in my time, I love that question because I glossed over it. In my timings, I didn't include the JIT overhead, which was on the order of, for the examples we did, 1.5 to 2 seconds. And I didn't include that because it would be cached, and you do that only once. And in any real application, the functions you care about are going to be called many times, or they're going to run so long that JIT time won't matter. But yes, the caching is absolutely critical for this working.
All right, we have another one. Folks at HPC centers are confused as to what to recommend to users. Any hint in the view of PyOMP?
I'm sorry, what was that? I didn't get that.
Folks in HPC centers are confused as to what to recommend to users.
Yes. Well, I must admit, that's what started me down this path about a year and a half ago, was talking to the people at NERSC and Argonne's, where I have the best connections, and their Python people. And they are confused because the solutions that are out there are really good. I'm not taking a dig at Ray or Dask or the other ones, but on a CPU, you really have to have multiple threads. And I'm not aware of a parallel multi-threading environment that can do what this can do. And so I want to get that out there and then help the people, interfacing with Python users at the DOE supercomputing centers and help them steer people to the right direction. Even if it's not PyOpenMP. I'm all about enabling users. But this is kind of a missing hole, parallel multi-threading. And I think that getting that out there, we can really help bring a lot of clarity to what advice to give people on Python and supercomputers.
All right, we have another. Can you talk about what kind of GPU support there is or plan to have, or maybe the broader question is the relationship between this and GPU?
Yes, so everything we have done, okay, so some of you may not know, OpenMP includes an interface to GPU programming. In fact, I'm writing a book right now, Programming Your GPU with OpenMP. So OpenMP does GPUs. And so everything we did, if you go back and think about the description of how we implemented PyOpenMP, all of that can be done with any OpenMP construct, including those GPU constructs. So we have not done it yet, but it wouldn't be a stretch, given the right backend LLVM support, to program a GPU this way. And the Intel LLVM, the one we ship with our products, has that GPU support. So we could potentially extend this to do GPU programming. But yeah, that's a big issue. When I look forward at what NVIDIA's doing in their relationship with ARM, what Intel's doing with we're coming out with our own discrete GPU, with AMD, and they already have their strategy of CPU integrated with the GPU, being able to step back and forth between the CPU and the GPU is going to be an absolutely critical skill for programmers to have moving forward. And that means Python programmers should have it too, because of course, we all want everyone to stay with Python.
All right, and I think the last one, people are asking for the GitHub repo of the project, and it looks like I didn't see it in the chat yet.
It's I don't think it's not on the GitHub repo yet. It will be. In other words, Todd and I have looked at it. There's every reason this can and will be open sourced, but the last steps haven't been gone through. I don't know when it will be there. I am hoping soon.
How about the slides of the talk? Are they available?
I haven't made them available yet, but I will talk with the SciPy people and figure out where to make them available. We have in the SciPy folder somewhere, there's on the proceedings, there's a presentation slide.
Right, I think
these slides will be available, yes.
All right, sounds good. So we'll make sure we make them available on the SciPy conference website.
Absolutely. Before the end of today, I'll try and make them available.
All right. I think we're out of time, but join me, everyone, in thanking Tim. And I'll go ahead and end the session in a minute.
Okay, thank you.